Have you ever wondered if the universe is sending us hidden messages? Gravitational waves are the ripples in space-time that could unlock the secrets of black holes and the origins of the cosmos. The hunt for them has just begun. Don't miss it. Imagine a stone tossed into a calm pond. The ripples it creates spread out across the water, carrying the energy of that impact far beyond the point where the stone landed. Now, think of those ripples on a cosmic scale. Only instead of water, they're traveling through the very fabric of space-time itself. These are gravitational waves, and they're caused by some of the most violent and energetic processes in the universe, like colliding black holes or exploding stars. Gravitational waves were first predicted by Albert Einstein over a century ago as part of his theory of general relativity. But it wasn't until 2015 that we managed to directly detect them. This discovery was monumental, opening up a whole new way of observing the universe, like adding sound to what we previously could only see. Scientists are thrilled because gravitational waves carry information about events that light or other forms of radiation can't reach, giving us a deeper understanding of how the universe works. With recent advancements in detection technology, we're now able to observe these cosmic ripples with unprecedented precision. This is more than just a scientific milestone. It's the dawn of a new era in astrophysics, where the mysteries of the universe are closer to being unraveled than ever before. Detecting gravitational waves is one of the most challenging tasks in modern science, and to understand why, we need to dive into both the technology and the nature of these waves. First, let's consider the phenomenon itself. Gravitational waves are incredibly faint, even when generated by massive cosmic events like black hole collisions. These waves stretch and compress space-time as they pass through, but the effect is minuscule. To give you an idea, the most powerful gravitational waves we've detected so far cause distortion smaller than a fraction of the diameter of a proton. This means our instruments must be incredibly sensitive, able to detect changes on a scale that's almost unimaginable. This brings us to the technological challenges. The primary tool we use to detect gravitational waves is called a laser interferometer. The most famous of these are LIGO in the United States and Virgo in Italy. These facilities use lasers to measure tiny shifts in distance as gravitational waves pass through Earth. But there's a catch. These instruments need to be isolated from almost all other forms of vibration. Even a truck driving miles away or a slight breeze could overwhelm the delicate measurements. To deal with this, the detectors are housed in vacuum chambers, and every component is meticulously designed to minimize interference. However, that's just the start. Gravitational waves come in many forms, depending on the source that generates them. Some are short bursts from cataclysmic events, while others might be continuous signals from spinning neutron stars. Distinguishing these faint signals from the background noise of the Earth's environment, and even the instruments themselves, is an enormous challenge. Researchers spend years refining algorithms and methods to filter out the noise and extract meaningful data. Moreover, there's the problem of scale. Earth-based detectors like LIGO and Virgo can only pick up certain frequencies of gravitational waves. There are other, potentially even more interesting waves that we simply can't detect from the ground due to interference from seismic activity and other factors. That's why future projects, like the space-based LISA mission, are being developed. By placing detectors in space, far from Earth's noisy environment, scientists hope to observe a broader range of gravitational waves. In summary, the hunt for gravitational waves is a monumental scientific effort that pushes the boundaries of what's technologically possible. It's like trying to hear the faintest whisper in the middle of a roaring crowd. But despite these challenges, every advancement brings us closer to understanding the universe in ways we never could before. The excitement around this field isn't just about overcoming these hurdles. It's about the incredible discoveries that lie on the other side. The journey to understanding gravitational waves is a story that spans over a century, beginning with one of the greatest minds in science, Albert Einstein. In 1915, Einstein published his groundbreaking theory of general relativity, which redefined our understanding of gravity. Rather than being a force that pulls objects together, Einstein proposed that gravity is a curvature of space-time caused by mass. Imagine space-time as a flexible fabric. When massive objects like stars or planets are placed on this fabric, they cause it to bend, creating what we perceive as gravity. Einstein's theory also predicted something extraordinary. When massive objects move, they can create ripples in this fabric of space-time, much like a stone creates ripples in a pond. These ripples are what we now call gravitational waves. But for decades, they were purely theoretical. Einstein himself doubted they'd ever be detected because he believed the waves would be too weak to measure. Fast forward to the 1960s, when scientists began to seriously consider how to detect these elusive waves. Joseph Weber, an American physicist, was among the first to attempt this. He built massive cylindrical detectors, essentially giant metal bars, that he hoped would resonate when struck by a gravitational wave. Unfortunately, Weber's experiments didn't yield conclusive results, but his pioneering efforts laid the groundwork for future research. The real breakthrough came with the development of laser interferometry, the technology behind the modern detectors like LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of two enormous facilities located thousands of miles apart in the United States, one in Washington State and the other in Louisiana. Each LIGO observatory has two long arms, 4 kilometers each, arranged in an L shape. Lasers are fired down these arms, and the light is reflected back by mirrors at the ends. Under normal conditions, the light waves return in perfect sync. But when a gravitational wave passes through, it stretches one arm and compresses the other, causing the light waves to go out of sync. This tiny difference is what LIGO measures to detect gravitational waves. The scale of this achievement is hard to overstate. The first detection of gravitational waves happened in September 2015, a century after Einstein's prediction. The waves came from two black holes, each about 30 times the mass of our Sun, spiraling into each other 1.3 billion light-years away. When they collided, they released energy equivalent to 3 solar masses in a fraction of a second. This energy traveled across the universe as gravitational waves, eventually reaching Earth and being detected by LIGO. It was a historic moment, confirming Einstein's theory and opening a new window into the cosmos. Gravitational waves are generated by some of the most extreme events in the universe: collisions of black holes, merging neutron stars, and even the rapid spinning of pulsars. Each type of event produces waves of different frequencies and amplitudes, carrying unique information about the sources. This makes gravitational waves a powerful tool for astrophysics, allowing us to study objects and phenomena that would otherwise be invisible or difficult to observe using traditional methods like light or radio waves. The success of LIGO has sparked a global effort to enhance our gravitational wave detection capabilities. Projects like Virgo in Italy and the planned LISA mission in space are designed to complement and expand on LIGO's discoveries. Virgo, which operates on the same principle as LIGO, but with different technological tweaks, has already contributed to several significant detections. LISA, the Laser Interferometer Space Antenna, will take the hunt to space, where it can observe gravitational waves that are too low frequency for ground-based detectors to detect. In summary, the history of gravitational wave research is a testament to human ingenuity and perseverance. From Einstein's initial predictions to the cutting-edge technology of LIGO, each step has brought us closer to understanding the universe's most violent and mysterious phenomena. Gravitational waves are not just a confirmation of a century-old theory. They're a new way of listening to the cosmos, offering insights into the nature of space, time, and gravity that were previously beyond our reach. The hunt for these waves is still in its early stages, but it's already transforming our view of the universe. In the ever-evolving field of gravitational wave astronomy, one of the most remarkable breakthroughs came in 2017 with the detection of a gravitational wave event known as GW117817. This event didn't just mark a milestone for gravitational wave detectors, it fundamentally changed our understanding of the universe. GW170817 was the first time scientists detected gravitational waves from the collision of two neutron stars, ultra-dense remnants of massive stars that have exploded in supernovae. Unlike the black hole collisions detected before, this event also produced electromagnetic radiation, which was picked up by telescopes around the world. This combination of gravitational waves and light made GW1717 a watershed moment, launching a new era of multi-messenger astronomy. The implications of this discovery are profound. For one, it confirmed that neutron star collisions are a primary source of heavy elements, like gold and platinum in the universe. The cosmic fireworks from these mergers scatter these elements across space, seeding future generations of stars and planets with the ingredients for life and civilization. Moreover, the ability to detect both gravitational waves and electromagnetic signals from the same event has provided an unparalleled opportunity to study the universe. By comparing the speed of gravitational waves and light, scientists were able to confirm that they travel at the same speed, as predicted by Einstein's theory of general relativity. This discovery also allowed researchers to pinpoint the exact location of the event in the sky, leading to an unprecedented collaborative effort involving over 70 observatories worldwide. The breakthrough of GW170817 didn't just open a new chapter in gravitational wave research, it bridged the gap between different types of astronomical observations. It's a glimpse into the future of astronomy, where we'll be able to study cosmic events in ways that were previously unimaginable, combining signals from different messengers to paint a more complete picture of the universe. This event has set the stage for countless discoveries yet to come, providing new insights into the most mysterious and energetic processes in the cosmos. Gravitational wave detection has revolutionized our understanding of the universe. From the early predictions of Einstein to the groundbreaking detections by LIGO and Virgo, we've unlocked a new way to observe the cosmos. These waves, ripples in space-time created by cataclysmic events like black hole mergers and neutron star collisions, offer insights into the universe's most violent and mysterious phenomena that were previously out of reach. The historic detection of GW170817, where gravitational waves and light were observed together for the first time, marked a significant leap forward, bridging the gap between different forms of astronomical observation. This event not only confirmed key theories in physics, but also revealed the origins of heavy elements and set the stage for future discoveries. In summary, gravitational wave astronomy is not just adding to our knowledge, it's reshaping it. As we continue to detect these cosmic ripples, we'll uncover more about the universe's deepest secrets, expanding our understanding of the cosmos and our place within it.